Welcome back. In our previous lessons, we established a foundational truth in thermal physics. When a solid material is heated, it expands, leading to a change in its linear dimension, its length. We defined this change per unit length per degree rise in temperature as linear expansivity. But what happens if the material isn't just a simple wire? What if it is a flat metal sheet or a solid block? Today, we are moving beyond just length to explore how heat affects a material's entire surface area and its total volume. Let's look at a rectangular metal sheet. A rectangle has two linear dimensions, a length L1 and a breadth B1. Its initial surface area, which we will call A1, is simply L1 multiplied by B1. Now, imagine we heat this sheet, raising the temperature from T1 to T2. Because of linear expansivity, the length expands from L1 to L2, and simultaneously, the breadth expands from B1 to B2. As a result, our final area, A2, becomes L2 times B2. Because both dimensions have stretched, the final area is obviously greater than the initial area. This proves that an increase in temperature directly causes an increase in the material's surface area. In physics, we call this area or superficial expansion. Just as linear expansivity tracks the change in length, superficial expansivity, represented by the Greek letter beta, tracks the change in area. Think of it this way. If you have a unit area of exactly 1 square meter, whatever fractional increase occurs in that area when the temperature changes by 1 degree Celsius or 1 Kelvin is its superficial expansivity. So we define it this way. Superficial expansivity is the change in area per degree temperature change. Mathematically, we write it as beta equals the change in area, delta A, divided by the initial area, A1, times the change in temperature, delta T. Its unit remains per Kelvin or per degree Celsius. Now, without going into too much complex detail, we can extend this exact same logic into 3 dimensions. If an object has length, breadth, and height, it occupies volume. When heated, all 3 dimensions expand, shifting the total volume from V1 to V2. This brings us to our third type of expansion, volume, or cubic expansivity, represented by the Greek letter gamma. Cubic expansivity is defined as the change or increase in volume per degree change in temperature. The mathematical formula mirrors the others perfectly. Gamma equals the change in volume, delta V, over the initial volume V1 times the change in temperature, delta T. To summarize today's lesson, expansion isn't limited to just one direction. Linear expansivity, alpha, governs expansion in length. Superficial expansivity, beta, governs expansion in area. And cubic expansivity, gamma, governs expansion in volume. Now, here is an exciting secret of thermal physics. Because area and volume are built directly from linear dimensions, alpha, beta, and gamma share a direct, elegant, mathematical relationship. How do we prove this arithmetic connection? And how can we use it to solve complex exam problems? We will establish and prove that relationship in our very next video. Thank you for watching. And remember to follow the Udimking Education Foundation on our WhatsApp channel and social media platforms for more step-by-step tutorials. See you in the next class.
Udimking Education Foundation. Building confidence, ending examination malpractice for a better tomorrow.
We are building a better tomorrow.
Join us in shaping futures through integrity and education.